this experiment, we will be discussing about loss of prime mover and how we can apply reverse power protection to protect a synchronous generator. So since already we have discussed, what happens is when there is a loss of prime mover, the three-phase generator will start to behave as a motor. So generator is now going to work as a motor. So when it is working as a motor, it is now a balanced load. So the current drawn by these three lines from the grid will be the same. So the reverse power protection is always a single phase protection. It's not a three-phase protection. Why it is a single phase protection? Because current drawn by the motor is a balanced load. So here this is the potential transformer and this is our current transformer. So the input to the relay, that is device number 32 or 92, is a directional relay or anti-motoring protection. So the input comes, there are two inputs to this relay. One input comes from the voltage transformer, another input comes from the current transformer, and it measures the angle and direction between the voltage and current, and when the direction reverses, it issues a trip signal to the circuit breaker. So now let us analyze this circuit diagram. So here this is our prime mover, and the prime mover is coupled to the generator, and this generator, this is the stator winding. Now this is our grid. So this portion here, the synchronizing module is connected to the power source. So this is our grid. So here what we are considering is, we are considering a system where we have a turbine. This is our turbine. This is our turbine. The turbine is connected to a generator. The generator is synchronized to the grid. So in normal condition, the CR1 contact will be closed. And when it is synchronized, it will be producing the rated current. So this is, the generator is now connected to the grid. In the lab class, the grid is nothing but our supply. So our supply is acting as the grid. So generator is producing power and it's supplying rated current to the grid. So this is the setup. So once you understand the setup, so now let us understand how to do the experiment. So what we have to do is, first thing that you have to do is, after you give the connection, you have to make this turbine run at near to the rated speed. So here let us say the rated speed is 1800 rpm. So first make the turbine run at 1750 rpm. Then adjust this exciter and make this voltage close to 220 volts. So this is the next step. So it is now producing the rated voltage. Now after you do this, what you have to do is, we have to adjust this supply. We have to adjust this supply, and as we adjust the supply, you have to see these lamps. So when the lamps, slowly the lamps will dim. When all the lamps are off, what we have to do is, we have to close this switch, not this switch. We have to close this. We have to close the synchronizing switch. We have to close all these switches. When the lamps are dark, we will close these switches, and what will happen is, now CR1 is normally energized. So CR1 is contact is already closed. So that means now we have connected the generator, we have synchronized the generator to the grid. Now the generator is supplying the rated current to the grid. So this is our grid. This is our grid now. Now how do we generate the fault? Now this is the important thing. How can we generate this fault? So in order to generate this fault, what we have to do is, we have to slowly, we are generating the fault of a turbine. Now here what we cannot do is, we cannot suddenly turn off the generator. So what we do is, we go to this power supply and slowly reduce the voltage and make it to 0. Slowly reduce the voltage. Now the voltage will be 220. Slowly reduce the voltage and bring it to 0. And once you do this, actually you are creating the fault, and that means the fault of the turbine is created by playing with the power supply. Now once you do this, what will happen is, this is our current transformer. This is our current transformer, and this is our voltage transformer. You can see the terminals A1, A2, A3, A4. So these are the inputs to our relay. So when you go to the next diagram, you can find A1, A2, A3, A4 here, which are the inputs to the reverse power relay. Here we are using the reverse power relay. The reverse power relay will check the direction of the power. Now here I already told you what we have to do is, in order to understand this, we have to draw these symbols here. So this will be the contacts of the CR3 contactor. Already I've explained this in our first experiment, so you will be knowing this one. So here we have the coil CR1. So here we will be having the coil CR1, and here we will be having another coil which is CR2. So CR1 and CR2 are connected to B1 and B2. Then here in across B2 and B3 we will be having a switch, and then we will be having the contacts of CR3. Sorry, the coil of CR3. So this is the coil of CR3. So this is connected across the terminals B3. So under normal condition, what would happen is, there will not be any output. This contact will remain open, and this contact will also remain open because this switch, the CR3 is controlled manually. So we are first opening this switch to understand the working of the relay. Now what is the only direction the current can flow? The current can flow only through this direction. Only through this direction. That means CR1 and CR2 are energized. So let us go back to the previous circuit. So here you can see CR1 and CR2. So CR1 and CR2 under normal conditions are energized. So energized means this contact is closed and this contact will also be closed. So this is the normal condition. Now when you are simulating this fault, when you are turning this power supply and bringing this to zero, what would happen is the power would reverse. You can see that you can monitor the direction of power in the wattmeter. So now what will happen is, under normal condition the direction of power will be in this direction because the generator is supplying power to the grid. Now when you are slowly changing this power supply and bringing to zero, you can see that the direction will reverse. That means the generator is now starting to work as motor. So when the direction starts to reverse, what you can see here is this contact would be closed. If this contact closed, you can see a red color light here. So this red color light indicates that the relay has sensed the fault, but it will not take any control action because this contact is still open. So what I want you to do now, close this contact, close the switch, CR3 switch manually. That means this contact will close. Here CR1 coil will energize. When CR1 coil energizes, this contact will close for holding and this contact will open. So when this contact opens, CR1 and CR2 will de-energize. So when CR1 and CR2 de-energizes, what will happen? These closed contacts will become open. So what we have done, now we have isolated the generator from the grid. So when you disconnect CR1, you are isolated the generator from the grid, and you are also opening the contact here so that the current in the excitation is also zero. So this is how the circuit works. So the circuit is very simple. Two things you have to understand: how to create a fault. Here we are creating the fault by playing with the supply. So when you bring this to zero, you can monitor this wattmeter. The direction will change. So when the direction changes, this relay output will be closed, and this relay output is closed, and when you manually close the CR3 contact, this contact will close, CR1 and CR2 will energize. So the idea is, the fault is created by playing with the supply, and the control action is opening CR1 and CR2 to isolate the generator from the grid. So this is reverse power protection. Now let us go to the next circuit. The next circuit is over voltage protection of synchronous generator. Now the question is, how do we get over voltage in a synchronous generator? You normally do not get, because we have already studied the concept of load frequency controller and automatic voltage controller. So these two controllers will make sure that there is no over voltage and it will take the control action. But it is possible that these controllers are faulty. These controllers may be faulty, or you have bypassed this controller and you are now using manual operation. So due to these reasons, there is always a possibility that there might be over voltage in a synchronous generator. And what will happen if there is a over voltage? It will damage the insulation of the generator. And another reason is loss of load. If the sudden loss of load will also lead to over voltage of generator. So here this is a three-phase protection and this is a three-phase potential transformer, and this three-phase protection transformer is connected to a device 59, which is nothing, which is a over voltage relay. So the input of this relay is going to come from a voltage transformer. So let us go to the experiment. It's very similar to the previous experiment. So this is our turbine, this is our turbine, this is our generator, and this is the stator winding, and this is the synchronizing module. This one is our synchronizing module, and this is our grid, and this is our grid. So what happens, the mechanical energy is converted into electrical energy, and the electrical energy is produced by this generator is given to the grid. So the direction is now in this particular direction. So it is generating and it is producing full load, and it is producing the full load current, which means it is supplying to the grid. Now what we are trying to do here is, I am not going to repeat again the operation. As you all know, first we have to make the turbine run close to the synchronous speed. Then we have to run this, make this exciter produce voltage closer to 220. Then we have to slowly play with this supply, and we have to make sure the lamps are dim. When the lamps are dim, we are going to close these contacts, and this CR1 is manually closed. We are going to close this switch manually. So when you close this switch, CR1 contacts are closed. So before synchronizing, we have to close CR1 contact, and once the CR1 contact is closed and after synchronizing, the generator is now synchronized to the grid. Now the question is, how do we create the fault? Here we are going to create the fault by suddenly removing the load. That means you are going to disconnect the generator from the grid. We are going to disconnect the generator from the grid. How to do it? Manually open the switch S1. Manually open. When you open the switch S1, what will happen? The CR1 contact will be open. When the CR1 contact is open, what will happen? You are disconnecting the generator suddenly from the grid. When the load is suddenly disconnected, what will happen to the voltage? The voltage will increase and it will result in over voltage. Now what happens when there is over voltage? You can go here. These are the voltage transformers, and these are the terminals of the voltage transformer, and you can see here the terminals of the voltage transformer are connected to a over voltage relay. So here I need not again explain this circuit. Many times I have explained this circuit. So here we have CR3 contact. Here we have CR3 contact. Now across B1 and B2, if you go and watch across B1 and B2, now we have only CR2 contact. Here we have CR2 contact. So this is CR2 contact. Here we are using CR1 to produce the fault. So this is CR2. Let it try to, and then here we have a switch, and this is the coil of CR3. So this is how it is connected. So under normal condition, what will happen? This is CR3. So this is CR3. So under normal condition, this contact will be open. CR3 contact. This is the contact of CR3. So this contact is also open. So only direction the current can flow is through CRB. So CR2 will be energized. This we already understood. So when CR2 is energized, this is the CR2. So what will happen is this CR2 contact will be closed initially. So when there is no fault, the current will be flowing. The current will be flowing through. This is shorted path. So here you see the current is flowing bypass the resistor, and it is flowing through the closed contact. So this is the normal direction of current flow in the excitation circuit. Now when you disconnect the load, what will happen is the over voltage. Now how do we reduce the over voltage? In order to reduce the over voltage, we have to decrease the excitation current. How to decrease the excitation current? We have to just open this contact. When you open this contact, the resistance is included in the circuit. So the current will now flow through the resistance. So when the current flows through the resistance, it will be reduced. So when the current reduces, the over voltage will be reduced to the normal voltage. So here we have to learn two things. How to create a fault? The fault is created by manually opening CR1. What is the control action? Control action is to open this contact so that the current now flows through the resistance and the current is reduced. When the excitation current is reduced, the voltage will be automatically reduced. So here initially the current is flowing through CR2. So when there is a fault, what will happen? This contact will close and there will be a red color light. Yeah, the red color light indicates that the relay has sensed the fault, but it will not take a control action. So if you want it to take a control action, you have to manually close the CR3 contact. So this will be closed. When this closes, the current can flow. This current can now flow through this closed contact and it will flow through CR1. So when it is flowing through CR1, the CR1 contact is energized. So this coil will be closed and this coil will be open. So when this is open, CR2 is de-energized. So when CR2 is de-energized, this contact is open and the current is flowing through the resistor. So here the control action is to insert the resistance in the excited circuit. So when you insert the resistance, what will happen? The excitation current is reduced and then the over voltage is reduced and it becomes the normal voltage. Thank you.